The last video talked about the sampling distribution of p-hat, which is the sample proportion. This time we're going to talk about the other one we will really be studying. That's the sampling distribution of x-bar, which is for sample mean. So this would be like if I took a population and took many samples from that population and then took the mean of each of those samples and then made a distribution out of all of those means. Okay? That would be the sampling distribution of x-bar. So the two big things we need to know are the mean and the standard deviation for this sampling distribution. The mean is really easy, and it's represented notation-wise as mu x-bar. And we use the Greek symbol here because it really is a population because it's every possible sample mean. So this is the mean of all of the sample means. And it's just equal to whatever the population mean is. If I truly have a sampling distribution, whatever the mean of my sampling distribution is, it's going to be equal to the population mean. The standard deviation is a little bit different. The standard deviation of my sample means, my x-bars, is equal to the standard deviation of my population divided by the square root of my sample size, which is n. These are on the formula sheet. Okay, and in order to be able to use this formula, your 10% condition has to be met, meaning that my sample size can be no more than 10% of my population. So if I take my sample size and I multiply it by 10, that has to be less than or equal to my population size. Okay, so let's look at an example. Suppose that the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. Suppose we take an SRS of 100 high school students and calculate the mean number of movies viewed by members of this sample. So what is the mean of the sampling distribution of x-bar? Well, that would be if I took this population of high school students, okay, that's my population, and I took every possible sample of 100. And for every possible sample of 100, I calculated the mean of each sample. And then I took the mean of all those means. Well, that mean of all of those means would be equal to my population mean of 19.3. And the standard deviation, well, one, I need to check the 10% condition. So I would say 10 times 100. Well, I am pretty sure that that is going to be less than all high school students because that's my population. So there's my 10% condition. And so once that is met, I say the standard deviation of my sample mean is my overall standard deviation, my population, 15.8, divided by the square root of my sample size, which is 100, which means my standard deviation is going to be 1.58. Okay, now remember, this is not the standard deviation of the movies watched. This is the standard deviation of the mean of the movies watched. So, on average, the mean number of movies watched by my 100 high school students will vary from 19.3 by about 1.58 movies. Okay, so once you know how to calculate the mean and the standard deviation of the sampling distribution, then you're really ready for the most important part, which is being able to work from a normal population. Okay, that's the part that helps us out the most. And so let's say, what is the shape of the sampling distribution of a sample mean when the sample is taken from a normally distributed population? Your sampling distribution, if your population is normal, is always normal. Okay? Always normal. And your sample size doesn't matter if your population is normal. So our shape, if our population is normal, is going to be approximately normal with a mean equal to the population mean and a standard deviation equal to the standard deviation divided by the square root of the sample size. And does sample size matter? Not if your population is normal. Okay, so let's look at this. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the jars is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. So without doing any calculations, explain which outcome is more likely. Randomly selecting a single jar and finding the contents weigh less than 16 ounces, or randomly selecting 10 jars and finding that the average contents weigh less than 16 ounces. Okay, we're not doing any calculations at all. So the way we want to think about this is things that are less variable. Averages are always less variable than individual measurements, because when I take individual measurements, I, depending on my probabilities, have just a chance of getting some crazy value as I do of getting a value pretty close to the average. Okay, but when I take an average of, say, 10 values, my really high ones might average out with my really low ones, and I have more of a chance of things kind of evening out and being closer to one another. So averages are much less variable than individual measurements. So if my average is 16.1, my mean, and I'm looking for something less than 16, then I'm probably going to have a better chance of getting that one if I randomly select a single jar, because it's more likely to be lower or higher than than the averages are. The averages are likely to be more kind of in the middle or less variable, closer together. All right, so let's find the probabilities of these events. If I want to find the probability of a single jar, and we're going to look at a new page, I know that the mean of all the jars is 16.1, and the standard deviation of all the jars is 0.15. So if I want a single jar, okay, to be less than 16 ounces, then that's just a normal distribution problem, because it said it was normal. And so I would draw my picture. Here's my mean, 16.1. Here is 16. So I'm looking for the probability that it's going to be down here. So z is equal to 16 minus 16.1 divided by 0.15. And I get a probability of 0.2525. Okay? That is, and I should have defined a variable up here, and I didn't. Let's let x be the weight of one jar. So this is the probability that x is less than 16, and it's about 25%. Based on my z-score and my formula, it's about 20, or my picture here, it's about 25%. Okay, let's let x bar be the mean weight of 10 randomly selected jars. And let's see how this is different. Well, one, I need to do it much like a sampling distribution, because I want to know, I'm no longer saying how likely is this jar to differ from other jars. How is this mean likely to differ from all the other means? So I need my new mean. And I know it's going to be equivalent to the original mean, the population mean. However, my standard deviation is going to be different, because my means are less variable, so my standard deviation is actually going to be smaller than it was. Okay, so, and I don't even have to work this out really at the moment. I could draw my normal, because I know that because my distribution was normal, my sampling distribution would be normal. 16.1. I'm still looking for less than 16. However, this is going to be a lot closer together this time. So my z-score would be 16 minus the mean of 16.1 divided by my new standard deviation, 0.15 divided by the square root of 10. Okay, then I say, what's the probability that x bar is less than 16? And before I do that, before I can use this and say that this is going to give me a valid answer, I need to check the 10% condition, and I did not. So I would somewhere around here need to say that 10 times 10 is less than all the peanut jars. Okay, so here's my mean. I take my z-score I get from this. I plug it into the calculator, and I get 0.0175, which backs up my original thing, because notice that this probability of one jar being less than 16 is quite a bit higher than the probability of the mean of 10 jars being higher than 16. And this is about 25%, and this is about 2%. So there's a much bigger chance that my single jar is going to be less than 16 than the mean weight of 10 jars. Okay, so check your understanding. That's it for, pretty simple, straightforward about the sampling distribution for a mean. So check your understanding. The probability that x is greater than 270 will be 0.4013. The probability, that does not go with this question. The mean of my sampling distribution here, of sample means, it's going to be 266 days. Okay, check your 10% condition here on number 3. Their sample size is 6, so I say 10 times 6 is 60, which is less than the number of pregnant women in the world, or even in the United States. And so therefore I can do my standard deviation. The standard deviation of my sample mean would be my original standard deviation of 16 divided by the square root of 6, which is about 6.532 days. And in number 4, it's asking me, alright, well, what's the probability that the mean of these 6 women is greater than 270? And I'm expecting it to be less than the 0.4. And in fact, when I do the math, it ends up being 0.2709.